Did he make it to China already?
Yeah.
No. Okay.
All right, it's 4:01, so we can get started, I guess, right, Bruce?
Go ahead.
Okay. So it's my distinct pleasure to introduce to all of you Professor Deepak Divan. He's a professor at the Electrical and Computer Engineering Department at Georgia Tech in Atlanta, Georgia, where he's also the Young E Piping Chair and the ERA Eminent Scholar and Director of the Center for Distributed Energy Systems. His field of research is in the area of power electronics, power systems, smart grids, and distributed control of power systems. He has worked closely with utilities industry and is actively involved in research, teaching, entrepreneurship, and starting new ventures. He's also the founder and chief scientist of Barentech in Santa Clara, California, and was president and CTO from 2011 to 2014, leading the company as it developed its suite of innovative distributed real-time control technologies. Dr. Divan has won many awards and distinctions, and among them, you can. I would like to highlight that the fact that he's a member of the U.S. National Academy of Engineering, and that he's also an IEEE fellow. So with that, I would like to get the control to Professor Divan so he can get started.
All right. Thank you so much for the kind introduction. And it's always a pleasure. I was just kind of trying to remember the last time I think I was out there was about 11 years back. So it's been a while. So glad to be there virtually to get my arm twisted by Phil crying to come and visit. I'm going to talk about really what we've been working on for a while now is really our view of the world. Power system is really a much more distributed and decentralized power system. And unfortunately, I don't necessarily have a lot of answers, but I have a lot of questions. And at least I want to share the questions with you, and maybe we can, work on answers together. So as I was introduced, I have spent a lot of time in industry as well as in academia. Still trying to decide what I want to do when I grow up, but what I learned at my last, stint at Verintech was that we didn't really know very well how to bring distributed and decentralized control to the grid in particular. So when I got a chance to come back and start the Center for Distributed Energy, that was really the focus. We kind of understood the changes were being driven by digitalization, decentralization, and decarbonization. But what does that really mean? I mean, utilities have a very different view of what change means from what industry is doing. And some changes are happening very, very fast, and others happening very slowly. Having been through trying to take technology to market, it takes decades in the utility industry. So therein was part of the problem. And so what we decided to do at CDE was really try to be a innovation center, incubation center, and an acceleration center, try to get things to market very quickly. Approach was necessarily holistic in terms of identifying real need and fundamentals. Didn't want to kind of accept conventional wisdom because conventional wisdom was centralized and didn't really give much insight into how to think in a distributed and decentralized world. And we wanted to focus on solutions that could be rapidly adopted and scaled. So we wanted to pay attention to the regulatory piece of it, to the the commercialization piece, the manufacturing piece, all of these elements that we wanted to kind of look at. The approach was, okay, you have a big asset base out there already. How can I augment the grid? We definitely needed to bring in more control. So what was the next generation of grid power electronics? That would also map over to the industrial side in terms of power electronics. When you went to a decentralized world, I mean, you were going to have millions of assets. How are you going to communicate with them? How are you going to, manage the edge when the edge has so much of intelligence? So that was, my learning out of Verintech was that, our biggest source of weakness was really the communications chain and how much it costs and what complexity it added to operations. So we worked on a system called Gamma. I'll talk a little bit about. Now, when you have millions of devices, all can work autonomously, what is the right approach to decentralized control? And I would not have believed this to be possible, but we actually showed this could be done when we were at Tech, and it kind of showed the, the opportunity. And then finally, I'm going to talk a little bit about energy access, because I think that if the grid were to be designed today, it would look very, very different from what it does. There's an opportunity to define that in emerging markets in Africa and other places, to develop, improve some of the technologies. What I think really changes things now are some of what are called exponential technologies, where technology performance levels are growing on a year-by-year basis while costs are dropping. And this includes not just power electronics and PV and solar, but also things like computation and energy storage and microcontrollers, social media, mobile pay. And these all have an impact in terms of how technology permeates and diffuses out into the universe. So we wanted to build the center kind of with that holistic, view. So let's just plow into what the grid looks like. I mean, the grid works very well, it was designed almost 100 years back. And those basic principles, at a time when there were no microprocessors, there were no sensors, there were no controllers, there was nothing, was still amazingly stable and amazingly good, and was able to expand out and scale across the continent. As we got microprocessors and we got communications and we got digitalization, we started trying to optimize the infrastructure more and more, and created all these layers of control, straight from the market layer to the control measurement layer and the device system layer, where we are actually doing protection and everything else. And we've been able to do a really good job. We've been able to maintain the processes that we had before, but now as we start looking at the changes that we are starting to see, including a lot of distributed energy resources coming in, we find that, maybe things are going to have to change a little bit. Let's kind of dive into that, into a little bit. We already see that centralized strategies start falling apart when the complexity of the system and the number of nodes to be managed and measured increases, dramatically. The processes that are slow, are not able to manage complexity in real time. As we expand the number of edge devices to millions of edge sensors and actuators and small inverters, how do you get real-time coordination across this when some of these assets are no longer owned by the utility but are owned by private individuals? Okay, how do you guarantee that you get compliance with what needs to be done? How do you do data management? How do you do cybersecurity? I mean, these are all very complex issues, especially when some of these technologies are migrating at phenomenal speeds. I mean, we're now seeing in some areas 2 to 3 year cycles, and utilities have a 15-year planning cycle. I mean, so this doesn't work that well. When you have a very complex top-down system, as we have in the utility world, they tend to be, very rigid. And when you have a resiliency event like a fire in California or a major, hurricane in Puerto Rico, these systems, kind of break down, and putting it back together can take a lot of time. So therein lies, part of the problem. The vendors are not supporting as much. The utilities don't do that much research. How do you manage change in this kind of an area? There's a few concerns that I have that are of primary importance. One is, real-time control when you have high latency in communication or loss in communication. We are building everything with the expectation that communications is going to be there and knowledge of the system is going to be there, and that is not guaranteed out here. When you have complexity in communication, you have poor knowledge of system state. How do you manage and control the system, especially through transients and the fast things that are happening out there? As you have technology migration, how do you manage that? I mean, when you have different vendors bringing new techniques in, what is that? What is the interoperability requirement that is there? How do you maintain situational awareness and at the edge, and how do you guarantee resiliency and reliability, especially at the edge? So these were very complex issues in our mind, and we've been kind of struggling with this in various places, I think utilities are starting to get very concerned about some of the things up here. Well, I work in power electronics, and that's a new thing as far as utilities are concerned. Many people would say that it adds control, and that's really very good. And we are building bigger and bigger and bigger systems. I mean, if you think about it, HVDC has been there for a very long time now. We have voltage source converters for HVDC light. And we are able to, integrate power from offshore wind farms, underwater cables. We are able to transfer power across China, many gigawatts across many corridors. We're able to do multi-DC, multi-terminal DC systems. Big problems out there. You have to build an HVDC circuit breaker, which is, problematic, but can be done. And you also have things like, if I have a big corridor carrying gigawatts of power, and something goes down, now what is the system reliability, and how do I maintain the integrity of the overall system? So we see a whole bunch of issues that are starting to come up out here. But I mean, there's no question that inverters are becoming a bigger and bigger percent of connected generation and load on the system. And the fundamental question of how do we operate a grid that is dominant with inverter-based resources, that's a major challenge, and continues to be something that needs to be addressed. So not only is this happening at the high voltage level, this is all we're talking about bulk power, very complex systems, takes a long time to build, long time to plan, and there's only a few people that are able to do this. But if you look at where we are going, we are able to do hundreds of megawatts now with modular low voltage inverters as well. And Tesla is a great example. I mean, they've built a 130 megawatt system in Australia in 6 months from start to finish, and they've done it again, I think, in a number of places now. And we see PV farms going up in the same way. So we're now seeing a second approach of doing control on the grid at the hundreds of megawatts level that is bulk power system, but that's built with modular low voltage converters. Very high level of resiliency, very high level of reliability because of availability that you get out there. But you have issues still. You have a lot of issues because, at high power levels, we still have, LCL filters out here. We have interactions with the grid. Most of these inverters tend to be, grid following inverters. Okay, and yet we are now seeing that when I have a lot of inverters on the system, I have loss of inertia. If I have loss of inertia on the system, okay, and I have a fault on the system, I need to be able to support the support the grid in some way. I mean, this is a very interesting chart. This is out of the first company that I had formed in Madison was a company called Soft Switching Technologies, and we developed the first internet-based power monitoring system. We had 200 monitors in the Northeast when the blackout occurred in August 2003. And we actually captured the dynamic frequency of the various parts of the grid. So this is, in Canada and the North, and this is New York City. And you can start seeing that, you have very significant frequency deviations, dynamic frequency deviations that occur when you have big faults on the system. And your inverters, how do they react to that? Okay, if you actually have a black start capability or a requirement, the inverters, how do you do that? I mean, that's a grid forming inverter versus a grid following inverter. And we have all these requirements that really we haven't really moved, very far in terms of the way we control and operate our systems. So, here's some examples of the issues that we are beginning to see on the grid in terms of very large, penetration of inverters. So large VSCs and modular multi-level converters, okay, have very complex interactions with the real grid. The switching frequencies are low, so you don't really have that level of control bandwidth. Okay, you have the LCL filter that we talked about here, and then we have the impedances of the system, and you have interactions with all the other generators and everything else. Here's a typical kind of impedance admittance plot of what the impedance looks like at different times. Okay, so as the network changes, the impedance profile changes, the stability changes, and all of a sudden, we see that we don't really have a very good handle on how the system needs to be controlled or operated. Okay, we see that when you have vendors, they are very secretive about the control principles they are using. So how does the system operator guarantee stability when the stability margins change so much with network connection, network topology? How do you guarantee it? Then and on top of that, we have protection mechanisms deep inside inverters that are not captured by the models. We have seen now several examples of near cascading outages that have been triggered by these inverter trips that are happening. And these are changing very, very fast. Okay, the utility is not very used to and accustomed to having change occur so very quickly. So, we can start seeing the scope of the problem, I think, that we are getting towards. And we are seeing that a lot of the tools we have are really not necessarily, there to be able to deal with it. Let's look at some of the additional challenges that we are beginning to see. I mean, system stability is one. We kind of talked a little bit about, the rate of change of frequency, Rokoff, and the fact that inertia is going down as you have more and more inverters, and you lose the inertia that the synchronous generators, actually are providing. You're familiar with the California duck curve, and the fact that as you have PV penetration, you get ramp rates that are very hard to manage and to protect against. As you get to the point where you have very high renewable penetration on the system, you also need to kind of start worrying about dynamic balancing. How do you know when you have sufficient energy to power your loads as the PV is fluctuating? How do you make sure that you have dynamic balance out there? That becomes fundamentally a very big issue. On top of that, if you layer the fact that some of these are prosumers, they kind of work for their own self, in terms of economic goals. How do you, meet the personal goals and still globally stabilize the system? This becomes another problem that needs to be dealt with. And finally, resiliency and communications and cybersecurity, are really fundamental problems out here in terms of the more intelligent devices you have, the more cyber security becomes an issue. The more you rely on real-time communications with low latencies, the harder it becomes when you have millions of devices out there. And if you are a top-down system and the bulk power system goes down, then you're without power for a very, very long period of time. These are some of the fundamental problems and issues that we see with the existing approach. So maybe the solution is distributed. So let's take a few minutes and kind of look at some of the aspects of distributed solutions. And is that even possible? Is that even doable? Is this just a pipe dream, that some academic, has and, will not go beyond a PhD thesis or two? So here's two examples of distributed solutions that we have developed and that are now commercial and available. So this was SmartWires, this was really triggered by the 2003 blackout, where we knew that if we could divert current flows from overloaded lines, we might have been able to avert a blackout. And we came out with this idea that can I have a clamp-on device that can be put on the transmission line that can change the impedance of the line, in a distributed manner. And if we could do that, you might be able to avert cascading outages and get better control of the system. We actually proved in our lab the ability to do this at thousands of amperes and at 350 kV level. That got the SmartWires company launched. It's taken a long time. We I think demonstrated the first devices at 350 kV probably in the 2008-2009 timeframe. They are this year. They're extremely successful. They're doing very, very well, and you can see some of the awards that they've been able to get. And this shows you the ability to kind of at transmission line levels to be able to inject dynamic impedances in the line and to be able to control power flows and to do power routing capability, all in a distributed manner. So this was a very good validation of distributed grid control. On the transmission side. On the distribution side, we kind of had started, I started Verintech, and we kind of developed a little volt-var control device that would go on distribution feeders. And this is a 0 to 10 kVAR var injection device, which sits on the secondary of a distribution transformer. This is example from Southern Company feeder, a 5 megawatt feeder, where we had 90 of these 91 of these devices in there. This shows you the voltage profile at these 91 points before the devices were deployed. And this shows you the voltage profile after the devices were deployed. So you can see that they're completely decentralized. They, don't need to communicate in real time. They'll communicate data, and set points will be communicated down, but these are, operate autonomously. So this also gave us the idea that it's possible to actually build, distributed and decentralized controls that can be deployed on feeders, and that actually the utilities will eventually accept. It took a while. It took a lot of convincing to get us there, but it certainly showed that this was doable. So when I came back here, we started working on different technologies that allow us to do this kind of control. One example that we've been working on for many years now is what we call hybrid transformers, where we are able to take a transmission level transformer or a distribution level transformer and add a small fractionally rated power converter in the neutral leg. Now this can use traditional power electronics that is readily available. And be able to achieve a lot of functionality that HVDC light can do, for instance, in terms of power routing, in terms of wire injection, in terms of voltage regulation, all of those capabilities. So from Georgia Tech, we built a device, a 13 kV megawatt scale, device, and interconnected 2 distribution feeders at 13 kV, and we're able to show that we could transfer power at will between the 2 feeders, this was a very interesting technology because it really shows a way to work with existing assets that the utilities have, and to be able to stiffen and augment the systems that they have, and to get the functionality of power flow control and everything else that they need. We are now building essentially a 22 kV 5 megawatt device for DOE, and we're hoping that this will transition to industry. We have an industrial partner who seems to be very excited about this, and we have utility partners who we are expecting that this will start going into. So this is another example of how do you bring control in it. One of the novel things that we introduced out here, which is really kind of universal in terms of the way we design these things, we call something fail normal. So we design these things in such a way that if the converter fails, this reverts back to a passive device. Okay, and this was very important for utilities to understand and accept power electronics, because when we started talking to them, they didn't want any power electronics because they thought the reliability of power electronics was much poorer than the reliability of the traditional power system components. Once we showed them this fail normal capability, they just got very comfortable, because this functions like a normal transformer when that device is down. In the case of smart wires, if one device is down, you have so many other devices in the picture that are able to provide control. And the same thing was true for Verintech as well. So we've kind of stuck with this as a philosophy when we're talking about control on the conventional grid. So this was one. We've also been working on a very exciting technology we call a multi-port soft switching solid state transformer, or S4T. This is power converter, but it's a very different kind of power converter. So it's got these input and output bridges. They look very familiar, except in the inside now we have a high frequency transformer, and these devices are all reverse blocking. And the way we've designed this is such that all the devices operate under soft switching conditions. So the efficiency is very high. We're running at 16 kilohertz, and we're still seeing 97% efficiency with 2 bridges and a transformer for high frequency isolation. Plus all our inputs and outputs are completely filtered. So it's a low EMI design, and it's completely bidirectional, and it can be made multi-port. And this there's a need, we think, for multi-port structures, that are, if you have PV and you have storage and you have grid, that's a multi-port structure. And today you have to have separate converters for all of them, and coordination and design. So it becomes a very expensive, approach. So we've kind of taken this technology and have leveraged that into a number of projects, which have triggered a lot of technology development. This thing is now heading towards commercialization as well. We're hoping that next year there will be product available in the market. in multiple applications that are really high impact and high volume. We've taken the same technology and have tried to see how do you scale it up in terms of voltage level as well. And so we've done a number of projects here. We've done a number of device developments. Nobody was building reverse blocking devices, so we've kind of picked up the cost of getting these devices built, the transformers built. And we've done several projects now. One was with Power America, where we showed essentially the ability to do a 5 kV DC microgrid. At the 50 kilowatt level, and with low voltage on one side and 5 kV on the other side. We've been working through an ARPA-E project to build a 13 kV class, so 7.2 kV phase line to neutral voltage, 50 kV a solid state transformer with DC and AC output on the other side. A very challenging project, because to get these stacked low inertia devices to work together was very challenging. But I think more important than that, everybody's been talking about doing these devices and replacing transformers. The fundamental problem, I think, is, the transformer isolates us from things like lightning strikes on the AC line. So you have to have a 90 kV BIL that transformers are able to meet very easily through installation design and coordination with the surge suppressor. With semiconductors, that's very, very challenging. But we've been able to do that. We've been able to demonstrate 90 kV BIL on the converter and able to demonstrate high efficiency. So this is very interesting topology. We've taken another example of it and built and got a project with Sunshock, where we are doing a medium voltage string inverter at 300 kVA and 4 kV, and we think that by doing the distribution at medium voltage and in large PV farms, we have shown that you can improve the efficiency by 2.4% and reduce the LCOE as well. So again, a lot of different kind of application opportunities that are built around the S4T, and I don't have time to cover all of them, but this gives you a flavor for it. One thing I do want to talk about, and this is the fact that as we start seeing a kind of a system that is more heavily inverter based on the grid, the question of how do you control them? And I'm sure that your team, your groups are working on this problem as well. But I think we see a few areas, the gaps that I think we need to all cooperate on and address. A typical inverter operates with a PLL and intercurrent loop. Okay, when you have large power swings, I mean, you can have problems with inverters. So typically we've designed these systems so that there's a generator in there that really forms the grid, and all the inverters kind of work, together with it. Now, when you start trying to form the grid through inverters, okay, and you're working with PLLs, it doesn't work very well because they all fight with each other. I know Phil's been working quite a bit on some of the issues associated with this, including some of the the resonators and everything else. But what we start seeing is that there's a couple of real big challenges in here. The inverters have to do a lot of decisions out here in terms of, are they in grid forming mode? Are they in grid following mode? How do I understand if there's generation surplus or scarcity? How do I balance the system? How does a load know that there's sufficient capacity on the system to connect the grid? And then how do you guarantee stability of the system, out here? So, what we've been trying to understand is, what is the right way to do it? I mean, one approach, of course, is, to do a virtual synchronous generator type of a control strategy for the inverter. In principle, that will, of course, work, but with all the same limitations that the synchronous generator has. So we've been kind of trying to boil that down to more fundamental, issues. And I think we've been kind of working on principles that we call collaborative control and this concept of self-aligning inverters, where the inverters can autonomously detect and operate either in grid grid following or grid forming modes. And you can actually, have almost variable inertia, adaptive inertia, and that allows you to track big changes, but still stiffen it. So it's very highly nonlinear control. What we find is that it really tends to stabilize the system. The analogy I like to give is, okay, it's like riding a tandem bike. The two people, are able to, ride through all kinds of, shifts in terms of terrain and the way and how they share power between them and what the speed is. And they do it without communication. So why can't I put that kind of intelligence in my inverter? We're all trying to design autonomous cars, very, very difficult problem. Why don't we design autonomous inverters that are able to do, all the things that we want to? So we want the inverter control to damp out the transients, to smoothly move towards the negotiated stage, but really do it with no system information or communications that is exchanged out here. And now it's looking like we are able to do that. And if we can do that, we can do microgrids very well. We can do grids very well. We can do inverter-based resources very well. So these are very challenging problems, I think. Let's talk a little bit about resiliency. I mean, as said today, we think about reliability all the time from a utility perspective. That's what they, definitely talk about. The problem is that reliability of 5 nines is measured on the bulk power system. And the last time I checked, there was no user connected on the bulk power system. And every consumer is actually on the distribution grid where the reliability level is a lot lower. And that's where you need the reliability. So in some sense, we kind of talk about flipping the model where we say the reliability and resiliency is obtained at the grid edge, and we use the transmission corridor to get access to low cost power when it's available from wherever it's available. Okay, so that's a fundamentally different model, but we don't quite know how to do that. If you take a look at a typical microgrid today, it's highly centralized in terms, they mimic a small utility, and they have centralized controllers that are doing dispatch and allowing everything to kind of work together. We see a more decentralized future where you can build an ad hoc grid, which can be just built with building blocks that you can, slap on as you need them. They kind of figure out what needs to be done. They can be very rapidly deployed, are mobile and transportable, are very resilient. And then, the second layer of that is really kind of what we call agile and fractal grids, where the system operates on rules that you can take an operating network and break it into parts, and the parts keep operating exactly the way they were, and you can then bring it back together and it coalesces together and continues to operate as the fragments are brought together. When we started talking about this seemed very, very esoteric, but we've now been able to show that you can actually operate systems where you can form a microgrid cluster automatically, and these things will start bottom up and come up, when the grid comes back, it'll reform. I mean, so all that stuff can be done and can be done, without much control, and can be done autonomously. So, that's starting to become very heartening, but, I think there is still a lot of questions that we do not know about how to implement decentralized grids. In fact, the worry is that we don't even know all the questions, forget all the answers, right? So we do believe in the principles of collaborative control, which we are now trying to really formulate, where, essentially edge devices follow simple rules. In this particular case, this is from Verintech, as I kind of showed you earlier. And individual devices act in real time to fulfill their individual, kind of objectives to the extent possible. We do not require or assume that there's any knowledge of accurate system, real-time knowledge of the topology of the system. We work with, set point kind of operation and slow communications for market functions. Okay, and device operation is based purely on local measurements and does not require centralized state estimation or dispatch or communication or anything else. If you see, signaling is, achieved completely through the network. There is no knowledge of neighbors or anything else. Collaborators, of course, have individual objectives, but are also providing all the support from a system perspective. One of the most important things that we've, recognized here is that when you have a multi-owner resource constrained system, and there is no guarantee that all objectives will be met at any given point in time, and it's perfectly fine. Okay, and if we kind of design accordingly all the elements, then everything kind of begins to work properly. And we've now been taking these principles and are kind of starting to design a whole bunch of microgrids and things like that that seem to work, quite well. I'll give you one example of it here. So, how do you do decentralized control of microgrids and grids, especially when you have multiple owners, each with price sensitivity, each with conditions that vary a lot. So, we've traditionally used power to frequency droop, as the control parameter. What we're doing here is we're kind of mapping price to frequency. So it's a price to frequency curve. Okay, and so what it does is allows, because frequency is a universal parameter across the microgrid or grid. Okay, every node at any given point in time, has real pricing information available, real-time pricing information available, and it can then act, against that or with that. And what we've now shown is that you can actually embed this in very low-cost, edge control devices, so that each device now has the ability to know what the price is. With slow communications, when available, it can understand a little bit of what the network looks like and who the players might be. Doesn't need to know that in real time. What we've shown is that this visibility, allows implementation of priority or market-based systems. It can operate over a wide range of resource surplus or scarcity. It can the intelligence is distributed to these low-cost nodes. And this continues to operate even when it's broken into smaller fractals. This can follow the same control rules. And it's very stable, and it works across a very wide range of demand to generation kind of ratios. Give you some examples of that here. So this is a small system that has been implemented, with multiple sources and PV and storage and I think 450 different consumers with different preferences, and a fairly high level of variability as far as the PV that is coming in is concerned. And what we see is that the frequency is varying, as the PV is varying, and the price is varying as the PV is varying. And as a result of that, you end up getting much better consumption pattern. When PV is available, you tend to want to use it more. We kind of migrate here from a generation follows load strategy to a load follows generation strategy, which in our mind is really very important if you're trying to to control this kind of a system. So, just the last thing out here, because it's really critical for distributed and decentralized systems to work, is you need to have a kind of technology agnostic, very low cost monitoring and edge control system, and there's nothing available. So we've developed something we call Gamma, which is the Global Asset Monitoring Management Analytics Platform. And it's based on a very simple device we call the Gamma kernel, which has, I/O, has computing, has 6 months of data storage, has power management, and has long-range Bluetooth that allows it to communicate with the data mule, which is really a smartphone or another device like this, which has a cellular modem. And we've shown that you can have almost a 1.6 to 2 kilometer range. This device is about $3. Okay, so we are now able to kind of communicate from pretty much anywhere in the world back into the cloud, and we kind of built end-to-end system that allows us to do that. And we've demonstrated this in a number of different ways. We have a DOE project now for asset monitoring, where we have a device we've developed that can monitor the current and voltage across transformers. Transformer sensors are not new. Typical transformer sensor might be $1,000. The transformer costs $1,000, so there's no way the utility is going to monitor this. We're talking about a $35 sensor out here that monitors 2 voltages, 2 currents, and can measure fault currents, can measure harmonics, can measure temperature, vibration, tilt, a whole bunch of different things, and can communicate that back to the cloud from anywhere in the world. So this is really kind of what you need to address all these issues for this to work. Here's an example of smart metering and distributed control that we've been able to do with this for an estimated BOM of about $12 to $15. So, I promised you that I'd talk a little bit about energy access. I want to do that because it's really important in my mind. All these elements kind of feed back into that, the whole area of decentralized control and everything else. But I'm presuming that we're going to have Q&A later. So with your permission, I'm going to kind of shift gears and move to a slightly different topic out here. And this is the area of energy access. What is energy access? You have 1 billion people living off grid, 3 billion in extreme energy poverty. Okay, they can't get their livelihood or anything. If you solve their energy access problems with the wave of a wand and give them OECD levels, that'll be another 3.7 gigatons of carbon emissions. That's certainly not okay. So what's the solution? If you talk to the World Bank, if you talk to the the national governments, they want to extend grid. Okay, well, it turns out that grid extension is not working out. If you look at sub-Saharan Africa, 95% of the utilities are not able to meet the capital and operating cost requirements. So that's not working out very well. If you look at microgrids and mini grids, I mean, the consumption is very poor because you have to still build a significant amount of scale out there, and you don't have the draw from the customers, so they can't afford it. So so what do? So your investment is sitting out there fallow and not producing anything. Very important curve out here, which kind of shows that if I plot all the the nations in terms of a human development index, we see this what seems to be a causal relationship with energy. I think it's the opposite. I think countries consume a lot of energy to get to a certain human development index, but not all of them do. And it looks like new technologies can allow us to completely change the equation in terms of getting to high human development index, but with low amount of electricity consumption. And that's where some of these new technologies, really come in. What are the challenges out here? These people earn less than $2 a day, so they don't really have a lot of buying power. They don't need energy. I never buy energy myself. They need the livelihood, the services that the energy enables. We talked about low purchasing power. That's really fundamental, in terms of their problem. They get hammered by, interoperability issues. They're very low tech users. They don't have any last mile sale commission and, maintenance facilities. So how do you kind of do this? There's a need really to scale, start small and grow it as needed. When we've looked at this, we've not seen good solutions. So finally, what we did is through IEEE Power Electronics Society, I launched a kind of an interdisciplinary global competition to develop scalable solutions to energy poverty. We call it Empower a Billion Lives. So this is kind of, sorry, I forgot this was here, but okay. So this is kind of, talking about the utilities in terms of grid extension and the mini grid opportunities, and the fact that both of these are really, not working out the way we want them to. So here's Empower a Billion Lives. So we started this competition. We had 2 tracks. One is a kind of a decentralized model for delivering services. One is a centralized model. We looked at technology, business model, social impact, and had to have field testing. We were blown away. We had 459 teams from 70 countries that submitted applications. We had 137 accepted proposals. We had 5 regional competitions all around the world. We eventually picked 82 teams, and then on to 23 finalists who all went and did field trials in places where meaningful, and then came into Baltimore in October 2019 to do to do the final competition. It was very successful. We distributed almost $500,000 in total funding and prize money to them. We saw some really interesting technologies come out of it: peer-to-peer community microgrids. How do you do AC/DC hybrid grids, stackable solar home systems, pay-as-you-go solar, mobile, kind of agricultural devices. The grand prize was, won by a team from IIT Bombay, who had a very interesting mix of technology in terms of supply chain and some standard designs, reference designs they had built. And they then trained women entrepreneurs to kind of build and distribute these solutions for solar lighting and everything else to students, and very powerful model. They've used the funds to start a new foundation to empower 100,000 entrepreneurs and impact 10 million users. So very inspiring. I was delighted to have been kind of seeding that and kind of heading that. Let's see what else we can do in this area. We've been working in this for a little bit. We have a technology we've been working on we call self-organizing nanogrids, where again this idea of you put the Ph.D. Not outside the box running it, but inside the box so that it doesn't need to be controlled. It can figure everything out on its own. So, this is a DC nanogrid concept where you can have everything sitting inside the box. You have a PV panel, you have some, useful loads out here, and then you can supply, 8 or 10 homes with 48-volt DC power and manage all the functionality, manage the billing, manage, everything is known about the system. And we're kind of building that right now with a 24-watt street light. We have a PV droop curve out here, and we have essentially full nanogrid functionality. From here, you actually have full knowledge of all the loads and what they're doing and what type of loads they're doing, and without communications. So you can see we're really trying to think holistically about the problem. If you load too many complex technology elements into it, it doesn't work very well. And then again, we manage the whole thing with the entrepreneur manager's smartphone, and this is kind of part of it. Another area of interest is this whole area of hyper efficient appliances, because if you look at major energy consumption, cooking is a very big consumer of energy, and transportation is the second one, and cooling is the third one. So these are really important elements, and we are extremely inefficient in how we use energy today, and we don't pay attention to how the people would want to use it. And we've been running some very interesting tests out here where we've shown that with a 25-watt panel, PV panel, we were able to meet all the energy requirements to cook 2 cups of rice at any point in time that you wanted, whenever you wanted it. That gives you an idea of how much of kind of reduction in energy usage is possible if you design the system optimally and use everything in the right way. A whole bunch of productive uses of electricity, everything from solar clinics to this is a solar chai stand. Okay, so much power to Starbucks. I mean, this is another way of doing it. Where you're doing welding, you're doing kind of machining, agriculture, transportation, hair cutting. This is really a big opportunity in Africa, and graining and things like that. So whole bunch of different applications, and the idea is, I call it frugal innovation. How do you apply the best technology to give them the easiest to use solutions that have the best characteristics and the lowest cost, all at the same time? That is really, I think, important. So we've been kind of talking about what are the attributes of this kind of a PE-based system. The grid systems are flexible, can use whatever available devices are there, has a very low cost base system that you expand as needed when you need it. Systems are formed bottom up, but can kind of manage market functions and can share power for load diversity, so you don't have the high cost. You have real-time dynamic pricing. You're balancing systems dynamically in real time without communication or deep knowledge of system state or topology, and you're ensuring stable and economic dispatch through that process. We are ensuring that systems are can be simple to install, distribute, maintain, and use, and you pay microfinance capabilities into it, and make unsophisticated users are able to use the system. Very tall order. It looks like something who would want to do, but I think the technology implications of this are fascinating. And if this can work properly in microgrids and nanogrids, it can eventually jump up into the main grid also. So last couple of slides, we see a very significant shift in grid paradigm. From centralized to decentralized, planned and scheduled to ad hoc and variable, coordinated, dispatched to autonomous, self-optimizing, and so on and so forth. And they all seem to be opposites. Okay, who is going to do that? The utilities don't really necessarily have the skill sets that you need on this side. How much of that needs to be automated in some way or the other? Remember something, we keep thinking that the experts know it all, but yet, if you look at the forecasts that the IEA has been making, they are completely off. Okay, they are, they thought that renewables would be 4.4% of total energy by 2030. by 2014, it was 28% of the total already. So they were just wrong by 600%. This is an interesting curve. This shows you the actual growth of PV. This is year over year IEA's projections on how solar is going to grow. Even when it's going this way, they think it's going to grow this way, right? So there's no surprise out here that it's very, very difficult to forecast the future. I talked to my friend Terry Boston, who's run PJM, and he says, 20 years back, no utility had a model that showed high penetration of solar, and they were not thinking of solar in their plans. And today, it's the preferred, solution when they can actually, get it. So we see a whole bunch of issues out here that one needs to, need to deal with, and the changes are coming, whether the utility likes it or, or not. And finally, I think of the, utility of the future really as a living ecosystem where you have these millions of edge devices that all work together to maintain kind of the infrastructure. First time and last time you'll see ants in a power electronics presentation. Okay, it's like a living ecosystem where you can, collaborate to do things that, otherwise would be impossible to do. And this is how we've done this. This is really, the control of the grid was based on completely collaborative control principles out here. We see a lot of change occurring, decentralization of intelligence and control decision making. We see price declines in key areas that are going to change everything. We see real-time pricing becoming available. We see that if you can reduce the cost of connecting millions of devices to the cloud to zero without technology obsolescence, that can change everything. We see that you can put dynamic control into devices and really augment system performance. And then we can build these systems to be cyber secure. So a lot of change. I'm glad we have so many young people out here, because our time is, I think, slowly kind of fading, but I'm hoping that we can leave the young generation to acknowledge these challenges and to come and with a very open mind be able to tackle them. So with that, thank you so much for your attention, and open it up for questions.
Thank you so much, Deepak. This was a great presentation. I really enjoy listening to all the things that you have to say about these issues. And yeah, so any questions from the audience? I think there is a question in the chat. I'm not sure. Should I read it, Bruce, or should I ask the person to just unmute themselves and read it aloud?
I'm not even seeing where the chat is right now.
There's
Yeah, you could read it, or Divan could read it, but you should read it before you answer.
yes.
I'm trying to find where the chat box is, sorry.
You click on chat.
Yeah.
I'm not seeing chat.
At the bottom of your screen.
Next to the participants.
Yeah, I've got the participants here.
Next to share screen.
I've got 172 participants, but I'm not seeing chat anywhere.
Well, you could read it, Alejandro.
Yeah, just read it to me. It's fine.
I think you have to stop sharing the screen. That's what the.
That may be what it is. Okay, I'll stop sharing the screen.
How about? Can you see it now? Chat
Yeah,
box?
now I can see it.
Okay, very good.
You should read it out loud.
All right, so I think that's the question is, you mentioned that a lot of technology changes are happening at extreme pace and outside of utility control. How do you think that state level RPS standards, or possible federal rules about decarbonization will play into forcing utilities to adopt new technologies? Yeah, great question. And clearly, I think if you look at how change has occurred, we can think about this occurring outside the regulatory envelope, but that's not true. Solar and electric vehicles and storage and wind are all occurring because there's a really good intersection of technology readiness with forward-leaning regulations. To get a new technology to penetrate into a market, you really need incentives at the first couple of years, if nothing else. So, so whether it's RPS standards that have kind of been forcing people to do it, or it's California that's forcing people to do it, or now, I think FERC's the 2022 regulation. These are all things that are certainly going to drive the utilities. The problem is the utilities have been thinking about change in a very much planned process kind of an approach where, this can take 15, 20 years, and it's occurring much, much faster than that. And, when I talk to utility kind of high level management people, they're little worried about what they're going to do and how they're going to be able to manage and how they're going to be able to respond to that. So I'm not sure if I've answered your question fully, but I mean, I do think that, the utilities are trying, not all of them, a few of them are trying very hard. A few of them are pretending that it's not happening and hopefully it'll go away, and it won't go away. So we're going to see some very interesting changes happening over the next 5 years, I think.
Okay, any other questions from the audience?
Yeah, could you talk about the role of demand response in the system, of how demand could be shaped depending on the amount of energy available over time?
Again, I'm sorry, this is a fascinating topic, right? This whole thing. I mean, I could talk for 3 hours, and this is the problem. But if you think of, I did talk about it, but didn't explicitly mention it. Today, demand response is used by the utilities to kind of do minor amount of control at the edges, 2, maybe 5%. That's the limit of it, right? And it's done essentially by a very small, limited number of players. We're starting to see, utilities in California, for instance, with very high number of EVs charging, where we're seeing some time of use pricing. We're seeing at least some effort to kind of modulate response, in some way. When you get to very high levels of EV penetration, it needs to be much, much higher than that. And our thinking is that it needs to move from the current paradigm, where generation follows load, to a new paradigm where load follows generation. Okay, and for that, I mean, real-time pricing is really critically important. So, when the thing that I showed in terms of using price to frequency droop to stabilize systems is completely demand response. Because, I mean, it really is based on that real-time price being available to your customers. And when we try to do some kind of role-playing and gaming on the system, I mean, that kind of information really gives the individual players the opportunity to plan better, to look at weather forecast, all the things that you want them to do from a market perspective, they can do, and they can become very much engaged in demand response. So I think demand response is a critical element, and I think we don't use it often enough and use it aggressively enough at this point. I hope you agree with me, but that's that's my perspective on it.
Yeah.
Anything else from the audience?
Well, I guess that also depends on storage, quick storage of energy. I mean,
Yeah, purely. I mean, storage is, I mean, we would have no problems in the world if we could just have, infinite storage available to everybody. Then there would be no problem, right? But
yeah, can you quantify what the limits might be and speculate in over 30, 50 years from now?
Yeah, so I mean, I think the bigger question in my mind is, I mean, if we could have storage everywhere, okay, we could run the grid exactly the way it runs right now, because every source could become dispatchable. And then you could run the grid exactly the way it is. But it would be very, very inefficient economically to do that. And you wouldn't get all the benefits that you want to. We are seeing now that, storage is critical, obviously. We're seeing already that PV plants are, kind of integrating storage automatically now. Large scale PV with 4 hours of storage is much lower LCOE, than just pure, because, you get dispatchability, you get a whole bunch of value stacking that you would otherwise, not be able to get. When we start looking at EV charging, it's going to go to fast charging. Okay, there's no option. So demand charges are going to become really problematic, or else peak loading is going to become problematic. So again, there's an opportunity to integrate storage. But if you have storage anyway, you might as well use it for other purposes in terms of grid support. So there's a whole bunch of now things that can happen. The problem is if the utility stays with its existing paradigm of managing everything centrally, then the whole thing starts falling apart. Right. So what are the rules by which individual devices operate? I tell my utility friends all the time, I said, if I drove my car the way you guys run the utility, okay, before I came out of the garage, I'd want GPS coordinates on every car in the state and what their plan of action is, where they want to go, so I could plan my day properly and optimize, 3 milliliters of fuel. Okay, that's not the right way to do this.
Right.
So that's kind of.
Thank you.
Okay, there seems to be one last question here on the chat box.
Yeah. So on the last slide, you mentioned no-cost cloud storage. How would no-cost cloud access be economically possible? Where does the funding come from? No, I didn't say, maybe I did, but no, I didn't say no-cost cloud storage. I think the idea was that there is no cost to connect to the cloud. Clearly, the cloud is that, and that's also really not true, because the model effectively, uses data mules that are actually operating and are paying the cost of that connectivity for some other purpose, like running a cell phone or doing something else. And so you're, because your data packets are so small, you're able to, kind of leverage that pathway and get to the cloud very easily. So we are essentially operating the system so that it can scale from a few devices to 1 million devices, and that's the beauty of the cloud. I mean, when I did that last time at Soft Switching, it was a nightmare. We had to get IBM involved because we didn't know quite how to handle ingest data from 1 million devices coming in. That's now suddenly become very easy and affordable, and the devices and the system scale so easily and so well. So it's not no cost, but the cost of that is picked up somewhere else. And so all of a sudden, your cost of managing 1 million devices anywhere in the world becomes very, very low. Hopefully that answers the question.
Thank you so much. We are at the 5 p.m. mark. So it's 6 p.m. in Atlanta, I guess, right?
I guess so.
Yeah. So I would like to thank you again, for joining us today. It was a great seminar. I mean, I learned a lot of things and I really enjoyed it. And, I hope the students also did and learn a few things along the way. So
absolutely. And if there's any questions, somebody has questions, let them send me an email. That's fine. I'd be happy to, try to think about it and answer them back.
That sounds great. That sounds great. Again, Deepak, take care, and we'll cross paths soon, hopefully when this whole thing is over. So,
yeah, you guys still owe me a dinner, right? I'd get a dinner normally, so you can either send it to me here or I'll come there and you can give it to me.
Exactly.
Sure thing.
Sounds good. All right, take care.
Bye. Bye.
Bye. Take care.
Bye.
Good night.
Bye.